So welcome back, everybody. I believe this is our 7th lecture in E340 542. As always, I need to remind you that the lecture is being live streamed and also recorded. And so you should be aware of that. Today, we're going to talk a little bit about some programming, model definition tools, and then we'll talk a little bit about we already did, in a sense, an SIRS model in the homework, and we went through that in some detail last week. Josh and Giuliano have sent you some boilerplate code to try to help out if you have to do things like find peaks and intervals between events. I hope that's helpful. Something that maybe I didn't emphasize enough, which I really encourage you to do, is that in a lot of ways, the simulations that we're doing are progressive. And so I would encourage you to keep in your arsenal of tools, when you write a simulation that does a parameter scan and plots the results, for example, keep that around and then modify that, build on the code. Because the lectures are really designed and the homework problems are really designed so that you first build a very simple model, then you do certain things with it in Python, then you do a little bit more with it in Python. And so the idea is that when you come to an in-class exercise, for example, you don't start from scratch. You say, oh, I worked on that problem. I already solved that problem to some extent. And so you have something that you can use as a template or a framework to build on. And so it's important to build those. You don't start again from zero each time. And I will provide examples, but really it's better if you do those things yourself, because you may solve the same problem about a parameter scan or finding peaks or finding something else in a different way from the way we do it in our examples. Just because our examples do it one way doesn't mean it's the only way or even the best way. You may be able to do it better. Okay. So today, as I mentioned, we're going to talk a little bit about the concept of an event. We'll talk a little bit about function definitions in Antimony. I mentioned fixed points very, very briefly last time. Come back to those, and then we'll look potentially at some other kinds of models. There are a whole framework of acronyms, SEIR, SEIQR, SIRD, and so on. We did one with SIRS and BSIRS models in the homework. And then depending on how time goes, we may start talking about in-host models of infection. And I'd like next week to try to do a paper replication. I want to try to pick a better paper and make sure everybody's prepared for that before we do it. The one that we were talking about, which was that one about vaccination, people had some very good comments in the homework about it. It's not a bad model, but maybe we can find something better. So if people find a paper they think we should try to replicate in class, I know I gave a homework assignment about finding a paper to replicate. But if you find one that you think is interesting, you want to suggest it to me by email, that would be great. So I want to come back to the idea of a fixed point. Ultimately, all of the simulations we're running consist of rate equations. That is, we have a variable, and here they're lowercase italic letters. We've been using chemical species names mostly, and uppercase letters, but we might have dx1 by dt equals some function of the state, dx2 by dt equals some function of the state. And again, the two things to remember are they're all first order ordinary differential equations in time. And secondly, the right-hand side is a function of the values of the variables and nothing else. There isn't any dependence on the time derivatives, for example, on the right-hand side, although I suppose there could be. But this equations have a particularly simple form. And a fixed point or a steady state happens when you find a set of parameter values and variable values for which things don't change in time. It's called the steady state because once you get there, you don't move away from it. And we've seen this in the simulations we do, where for epidemics, we either reach a state where everybody's been infected and there are no people being infected, where there's a constant level of infection, a constant fraction recovered, a constant fraction infected at any given time. We've seen situations in which we got oscillations, but those oscillations died out in time. We'll come to situations where you have continual oscillations, where the oscillations don't die out. And in those systems, those don't reach a steady state if we run them in time. But usually there's still a parameter value and a set of variable values where you do have a steady state. And so the steady state is simply evaluated by setting the left-hand side, dx by dt, dy by dt to 0. And then in principle, we have a set of functions and we have to invert those and solve for their roots. If the functions have very simple forms, we may be able to do that analytically, just algebra. In other cases, you may get what are called transcendental equations. It doesn't mean the roots aren't there, but you can't solve them in a closed form, write down the solution so easily, and you have to solve them numerically. And so that idea of a fixed point is critical to what we're going to do. What is also critical to what we're going to do, which we're not going to talk about now, is the idea of a stability of a fixed point. So let's take as an example, a very simple example. Suppose that I have no COVID. And so my situation is that I have some susceptible population, say the population of the United States, 330 million people. I have 0 people infected and 0 people recovered. And as long as I don't introduce any COVID, anybody with the infection, that situation will persist. And so S equals S0, I equals 0, R equals 0 is a steady state, a fixed point. However, if I introduce a few people with COVID and R naught is bigger than 1, then I'm going to get an epidemic. And so that clearly means that that fixed point at S0, 0, 0 is unstable. If I perturb it a little bit by introducing a few infected people, then I move away from that fixed point. If R naught is bigger than 1, and if R naught's less than 1, I move back to the fixed point. The fixed point is stable. And there's a simple mathematics of how you determine the stability of fixed points, which I'm not going to go into here, but you should be aware that fixed points come in 2 kinds, stable and unstable. And just have an eye out for that. Ask the question, if I perturb away from my fixed point, do I come back to it? That's always true for the long time solutions. Any fixed point you see at the end of a run is going to be of that kind. Or do I move away from it, which typically happens for fixed points at the beginning of simulations. And Herbert's textbook has quite a bit of the mathematics of how to determine whether fixed points are stable or unstable. And I hope maybe towards the end of the class, if I have a chance, we can talk about stability theory a little bit. In the past, I used to do quite a bit of it, and some people didn't enjoy the mathematics of it very much. And so I've tended to move away from presenting that material, but it's quite important, and it's not that complicated. So if you've had a little bit of vector calculus and linear algebra, so you know what a determinant is, then analyzing fixed points is straightforward. If you've never worked with determinants, then it's a little more challenging, which is why I'm not going to push it on you this moment. And then we talked about stochasticity, and in our ODE models, we always assumed that there was a single rate. In particular, the idea was that an individual who was infected at a given time, every individual who was infected at a given time infected the same number of additional individuals. That was our concept of beta. And in reality, infection looks a little bit more like the picture on the right. You have an infected individual who infects 3 people. One of those people infects nobody. One of them infects 1 person, 1 infects 2 people. Those 3 people who've been infected, 1 infects 1 person, 1 infects 2, and 1 infects 4. And so you get then what are called chains of infection. And somebody proposed to do as a project a replication of a nice paper that was doing these chain of infection models. Those are very interesting. They're not particularly easy to do in the Antimony framework, so I discouraged working on that. And not because it's not a good problem, but because it's a Pythonic problem. One of the things that's interesting is even if R naught and beta are the same for 2 diseases, the dispersal of the fraction of people infected can be different, and that can lead to interesting differences in the behavior of the disease. And so, for example, with influenza, the typical person who has influenza infects 0, 1, 2, or 3 people. Whereas with COVID, we really did have, at least according to Schiffer and Fred Hutchinson in Seattle, who's the big expert on this, you really do have super spreaders, where most people with COVID infect nobody, but a few people infect tens or hundreds of people. And that means that the statistics of the infection can be rather different, even though the mean number of people infected per person is the same. And clearly in our ODE models, you don't see that. And so you have to ask the question, when does that stochasticity of infection make a difference and when doesn't it? And one of the things that we looked at last time was that we found, and there were some homework problems trying to explore this a little bit more, that when the number of people who are already infected is small, then the stochasticity makes more of a difference, or when the total population is small. So at the beginning of an epidemic, when you only have a few people who are infected, what happens in terms of infectivity matters a lot. New Zealand and China were able to shut down the epidemic early and prevent community spread by taking very severe lockdown measurement. And they were able basically to turn the epidemic off, or at least delay it for a long amount of time. In other cases, you had things like cruise ships or prisons where essentially everybody got the disease. And so you can have very rapid spread. And so in these sorts of situations, especially early on, if that very first person with COVID who comes into a community doesn't give it to anybody, then there's no epidemic. And it's sort of an interesting question to ask, at what number, we know that if there are very few people, the stochasticity matters a lot. You can ask the question, at how many people does the stochasticity stop making so much of a difference? And that was really the question that was asked in the homework, and we did a little bit in class last week. Again, if you really want to do these chains of infection, you can do them in Python. And Python objects like lists and dictionaries are great for doing chains. Dictionaries in particular are a great way of doing, and lists are great ways of doing trees. And it would be fun to build some agent-based models of that. What we decided to do instead was to do something that's built into Antimony and Tellurium, which is that they have this Gillespie solver. And the Gillespie solver is designed for doing chemical reactions. Again, in chemical reactions, ultimately they're discrete. Two molecules come together, they either react or they don't. And that's a probabilistic event. When we write chemical rate laws, those rate laws really are describing probabilities of reaction. But of course, if you have 10 to the 23rd molecules, then those things average pretty well. If you're in a cell and you have a transcription factor that binds to a single binding site on the cell's DNA, that's either bound or unbound. There's no, it's a Boolean process. The gene is either turned on or it's not. And in those situations, the stochasticity can matter a lot. And the Gillespie algorithm was designed really to try to do that. And it basically pulls the individuals from the pool, atom 1 and molecule 1 and molecule 2. It then brings them together and rolls the dice and says, did they react or not, based on the probability of reaction. And that's actually pretty close to what we have in our infection experiment. It's not chains, so there's no spatial segregation, but it does say that when you have two people come in contact, one of them is infected and one isn't, that you have to roll the dice. There's a probability of infection, but not a certainty of infection. So you tend to get Poisson relations for probabilities. One thing that you might want to remember if you're going to use the Gillespie method is that in Antimony, well, actually in Tellurium, because it's in the Python side, you can say r dot set seed, and that will set the random number generator used by the Gillespie algorithm. So if you want to run the Gillespie twice and get the identical results, you have to pin down the random number generator, and that's how you can do that. The other thing that I wanted to add to the slide and then got distracted a little bit about was that you can specify how many points you want the Gillespie solver to give you. Just the way with the simulate, you can say start time, end time, number of steps. You can do the same thing with Gillespie. You can add a comma number of steps if you want. But intrinsically, Gillespie doesn't return values at fixed time intervals. It'll give you a pair, which is time and value as a pair, and the spacing may not be uniform. And that means that when you're trying to do things like stack, you have to be a little bit careful because the times for different simulations may not be quite lined up. So we did this nice exercise. Well, I don't know, nice. I think it's a nice exercise. I enjoyed doing it when I created that problem some time ago, where we did a simple SIR model and we ran it a number of times, say 10 times, and we changed various aspects of the simulation. We changed the number of initially infected individuals, the total population, and the R0. And we asked the question, when does it look like our ODE model, our deterministic model? When does it look different? And then in particular, how does it look different? And I think the key thing is if we come down here to the bottom right, and here I'm not plotting the number of recovereds because that's the number of recovereds is the initial number of population minus S minus I. So they're essentially redundant to add that. If we come down to the bottom right, what I see is that the time series for susceptibles going down and infecteds coming up is essentially identical to what I'd get for the ODE, modulo a little bit of jitter in the timing. And it's interesting that that timing is jittery. The vertical values are pretty narrow, but the timings have a little bit of jitter. And how many did I have here? I had 10,000 total population and 100 initially infected individuals. And so with that 10,000 total population, 100 initial infected individuals, I have an error perhaps of 10 or 15%. It's still substantial. But qualitatively, I don't see anything unusual. Everybody follows effectively the same trajectory. The final states are essentially the same. If I start with 10 individuals infected rather than 100, what I see is that I've always followed the same pattern of the epidemic. My final values are essentially identical, but the timing of the epidemic now becomes quite uncertain. I see that there's a lot of jitter. Sometimes my epidemic starts around day 10. Sometimes it takes till about day 20 to really get going. And if I ran that for more than 10 replicas, I'd find that there's some outliers where it takes a really long time to get started. And that's because this chain of infection at the very beginning determines how fast things get going. Once you get to 100 infected individuals, things are pretty reliable. But at the beginning, when you only have 10, there's rolling the dice makes a difference. For the same total population and the same R naught, if I now go to one initially infected individual, I see something different, a qualitative difference. If I start with one infected individual, I see a couple of replicas where there is no epidemic. That first infected individual goes to recovered before they infect anybody else. And so I have this straight line where I had one infected individual goes to 0. My susceptible population stays basically my initial value S0, and there's no epidemic. And that's the whole point of quarantining travelers and things like that, is to prevent that first person from spreading the disease. What you're seeing in this peak is what's called community transmission. And this is preventing community transmission. If I decrease my total population and start with one individual, I perhaps see a few more cases where I get no infection. But I also see now my lines in when I had 10,000 people were very smooth. Here I see some jitter in the time series in the vertical direction. My curves are no longer smooth, they're jagged. And that is a reflection of the total population, not the initial number infected. And so that's a new qualitative behavior that I'm seeing. If I begin to go further down and I reduce my total population to 100, I see some additional things that can happen. What I see with 100 is that even though I'm starting here with more infected individuals, 5 individuals, sometimes the disease still dies out. Sometimes it comes up. And what I see, interestingly enough, is that now in the state where I had a lot of people, either nobody got infected or essentially everybody who's going to get infected gets infected. Now I get these intermediate states where when the epidemic is dying out, sometimes it dies out sooner than you'd expect. And so I wound up with more uninfected individuals at the end than I would have thought I would. And if I reduce my total population even further, I can have situations in which I wind up with a substantial fraction of my individuals uninfected at the end, even though my expectation would be that almost everyone gets infected. And so as I decrease my initial number of infected individuals, I see first this uncertainty of timing, then the appearance of failure to infect cases where the epidemic dies out. And then as I decrease my total population, I see the appearance of first of noise in the values, and then the appearance of these intermediate states where even though I would expect either nobody or everybody to get infected, I get these intermediate outcomes where a few people get infected and then the disease dies out. And so it's worth, again, when I ask people to say, describe what you see, I'm going over this again because this is the kind of description that I'm hoping for. And since it only takes a few seconds to run one of these simulations, when I ask you to explore parameters, I do ask you to try to explore them in some detail. So in this case, we started out by setting S0 to 10,000 and then exploring what happens when we change the initial number of infected individuals. Then we kept the number of infected individuals, but we had to reduce it because 100 is going to be too big for some of these. Then we say, pick a case like the number of infected individuals is 10. Now we've reduced the total population and see what happens. And so we explore both of those parameters and get a sense of what all the possibilities are in this world of this very simple simulation. In the ODE model, there was really only one thing that happened. The only thing that mattered was R not bigger than 1 or less than 1. In the stochastic world, there are a lot of different things that can happen because of population matter. Are there any questions or comments about that before we move on? This is a pretty important caveat because in almost all the population modeling you'll see, people use the ODEs. And one of the things I like about Tellurium is that it's very easy to throw it into a stochastic solver, same model, and ask the question, how is it different? Okay, I mentioned that well, you should have gotten emails from Josh and Giuliano providing some easy code that's useful. I just wanted to remind you, and these slide decks, of course, are available to you, that there were a few things that we wanted to do. One of the things that we might want to do is iterate over an array, a numpy array. And so here was some code that iterates over an array to find the time at which the value is reduced by a half from its initial value, the time at which half of the population is infected. Something we're doing a lot are parameter scans. One way to do a parameter scan is to, well, here we're just plotting them. We're running the simulation, suppressing the plot and then plotting it at the end. It's not the most elegant way to do a parameter scan, but it's something that we use a lot. That's how those ones, we've done that quite a bit. Another thing is when we want not to plot time series versus parameter, but value versus parameter, for example, that time to half maximum, there are a number of ways you can do it. I tend to use VStack to build an array that we can then plot, but there are other ways of doing that too. Again, it's good to have examples of these in your own toolkit, solve the problems the way you like, and then reuse them, adapt. I gave you a homework problem. I don't know if people tried it. One of the homework problem was, I thought, quite a profound one. Came from PowerPoint slides that had been posted by somebody some time ago, Jamie Lloyd Smith. And he'd then, I think, had a paper where he published it as well. And he was looking, actually, Jamie, I don't know whether it's he or she, it's an ambiguous name, probably, maybe female. I guess I'm not supposed to say that these days, problematic. But they evaluated starting basically the question that we were asking from the picture that we looked at just a few minutes ago, which was, we saw that sometimes the epidemic dies out if the population was small and the initial number of people infected was small. And so here they say, what if you start with one infected individual? They don't specify, at least in the diagram, they don't specify how many the total population is. And they ask the question, what's the probability of the infection dying out? What's the probability of getting that horizontal line instead of the peak of the infection as a function of R naught? Clearly, if on average you infect 50 people, the probability that the infection dies out starting with one person is lower than if on average you infect 1.1 people. It also matters what the variance is. If you on average infect 2 people, but the variability in the number infected is very small, then the probability of die out is low. If you have, on average, infect 2 people and the variability of the number infected is very large, then the probability of die out is large. However, you still would expect the shape of curve to be similar. You know that if R naught is less than 1, you're guaranteed to die out. If R naught is very large, you expect that the probability of extinction is fairly small, but there should be some curve that connects these. So did anybody do this homework problem? And if so, what did they get? I'm not hearing a huge response. Drew, did you try it? Ryan, anybody?
I couldn't get to it yet.
Okay. Okay. I mean, it's possible. Maybe we should, Josh, do you have the code to do that problem? We did it last year.
No.
It may be worth actually working together to get this problem solved because it's actually pretty interesting. Let's see how we go with the rest of the class, and if people are interested. And would people like to try to solve this problem together? I'm not.
Yeah.
I don't. So somebody said. Bruce says yes. I mean, we can try. So let's come back to that. Let me cover the first part of the class, see what time it is, and then depending on how the time goes and and people's feelings go, we can maybe come back to this and solve it together. And Josh, you can be thinking about it in the background while I go on with the lecture. Drew, I'm sorry about your computer. Yesterday, I've been having more and more trouble with Zoom, locking up and doing unpleasant things on my computer. And yesterday I was on a Zoom call at 9 o'clock in the morning, and my computer locked. They could hear me, the video camera worked, the audio worked, but I couldn't even Control Alt Delete to get the task manager to come up. The only way I could get the computer off was to pull the battery. I wound up, fortunately, I pay for Dell expensive service for this computer because I depend on it. It took them 5 hours. They had to change the BIOS, rebuild the operating system, change the registry. It was really a mess. So we'll see. They promised me that my Zoom should now work. So we'll see how it goes. If it starts failing again, I'm not going to be happy. But I spent 5 hours on the phone with Dell yesterday because there was, as far as I can tell, driver incompatibilities with Zoom. So I'm sympathetic to the problem. All right. So I want to talk a little bit about some basic programming, and I want to talk again about first some simple programming concepts, which we talked about a little bit yesterday, but last week, but didn't go into detail about, and then some things that are a little bit more conceptual about what models are and what antimony is. And you may have heard me say before that antimony really isn't a programming language. It's a model specification language. Those are a little bit different. So mostly what we've been doing are specifying rate equations. And while any rate equation numerically has to be solved in discrete time steps, time 1, time 2, small delta t intervals, conceptually, the ordinary differential equation is describing something that's continuous in time. When we write ds by dt, we're describing that s is changing continuously in time, even if numerically we have to evaluate that in finite time steps. And so there is a concept of things that happen continually in time. And then the terminology for things that happen discretely in time is events. So getting older is a process that happens continuously in time. Being born or dying is a process that happens discretely in time. It's an event. Cell division is an event. Cell growth is continuous. And what we've looked at so far are computationally are continuous time processes, rates. But very often, biologically, we want to have a discrete change. We start with no infected individuals. We add an infected individual to our population. We start with nobody vaccinated. We start vaccinating people at a given time. We're modeling something inside the body. We give a drug at a particular time. We can certainly do that, and there's nothing wrong with doing that, by specifying the continuous time portion of our model in antimony, running the simulation using our simulate up to some time, then going into the Python, changing variables, changing parameters, and then running for more time. That's one of the reasons simulate doesn't reset time, but continues from the time that you finished, unless you tell it not to. But antimony does allow you to specify events within the network model description. And again, remember that these model descriptions are in fact descriptions. They're not programs. So for example, the order of the lines in your antimony specification, certain things matter, because if you say x equals 1 and then x equals 2 in the next line, it will set x equal to 2. So the latter one will overwrite the former one. But in general, if I specify rate law 1 and then rate law 2, or rate law 2 and then rate law 1, it doesn't matter. So that's somewhat different from procedural code. Within, and there is no fundamental so far sense of event, antimony has a very simple syntax for events. You can name them just the way you can name rate laws. And you do that by giving a name and then a colon after it. And then an event, the syntax is the word at, and then a parenthesis and a trigger, which is a logical expression, evaluates to true or false. And then there's another colon. And then you can have a list of things that you want to have happen. And you can have multiple things be triggered by the same event, separated by commas, and then you end that with a semicolon. So if we wanted to say A is the concentration of a molecule, and at time 15, we want to add 15 units to A, we write E1 colon at time greater than 15, A equals A plus 15, semicolon. So again, it's important to remember we could have said A equals A plus 15, B equals B minus 15, so on. So that's the basic concept of an event. Pretty simple to write down. It doesn't let us do things like loops in any fundamental way, but remember that biologically most things happen simultaneously, not sequentially. And there really isn't a concept of branching in loops of the kind we have in computer code. People who make an analogy between genes and computer code are making a very bad analogy. There are some similarities, but more differences than similarities. So let's try writing an event. So I'd like people to fire up Tellurium, and I'd like people to write a very simple network model. I hope you have something like that. Let's just say A goes to B at a rate K1 times A. B goes to nothing at a rate K2 times B. Just to give you some certainty about it, let's let K1 equal 0.2, K2 equal 1. Start out with A of 0 equal to 10, B of 0 equal to 0. And then add the event E1 colon at time greater than 15, A equals A plus 15. So I'd like everybody to try doing that. So is it clear what the little exercise is? Okay. So I'll let you all give a shot at that. And are people okay trying it on their own? I mean, no, sometimes I'll do the coding in parallel with you, but I think this one, I hope this one is simple enough that you can try it without my watching me code it. Okay, so why don't I give you all a couple of minutes to try that out, and I'll do a poll in a minute or two, and we'll come back to it. Okay. Josh, I'll be right back. I'm going to get some more water because I seem to have a froggy throat, so I'm going to get a little bit of water. People want a little bit more time, that's fine. If people have any questions about what the exercise involves, please let me know. Feel free to ask. Josh is here to help too. Take your time. So again, the exercise is to write a simple network model. A goes to B goes to nothing with the parameter values as given. Run that, see what it does, and then add the event at time greater than 15, A equals A plus 15, and see what's different about it. Okay, great. So does anybody want to tell me what happened? We can have you screen share if you like, or you could just tell me, what did you see? I can call on somebody if you like, or Colin, do you have what happened?
I can screen share if that might work better. So this is what happened in my model.
Great.
After I added the 15, the B had a second peak, basically.
That looks fine. Did other people get something similar?
Yep.
I mean, it's not the most sophisticated problem, but it's that's great. Okay, good. Thank you. So let's come back to it for a second. So that's what I got. And one thing that I actually have on the slide, but isn't really shown, which is that if I ran it for a long time, it would only increase once. And so that makes it a little bit ambiguous. The wording of the syntax is a little bit ambiguous. because time greater than 15, you might expect that every time, each time greater than 15, you added 15 to A, in which case A would go up, 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 up. But in fact, the way an event works is that it's a trigger, and the event triggers each time the trigger goes from false to true. So time getting to be bigger than 15 happens once. For time 0 through 15, it's false. For time 15 and greater, it's true. So the trigger goes from false to true precisely once. On the other hand, if I wrote something maybe not so sensible, E1 colon at sine, as in sine wave, of time greater than a half, B equals B plus a half, then every time the argument sine goes from being less than a half to being bigger than a half, we'll add B, we'll add a half to B. So why don't people actually try that? Here I notice I wrote E1, should have been E2. You don't want to name two events with the same name. That's going to cause a problem. Try adding the line to your code. Here I have it at E3, E3 at sine of time greater than a half, B equals B plus a half. Try that. And why don't people try that and let me know what you get? Again, if it's not clear what the question is, please feel free to speak up, either unmute or ask in the chat. So if you had the original simulation running, you're only adding one line, E3 at sine of time. So okay, does somebody want to show us what they got? Brian, can you do that? Is that all right?
I am actually having trouble like running it. I'll share my screen. The code doesn't seem to be working.
Okay, let's take a look together.
Yeah.
You should be able to screen share if you want.
Yeah. So like even in the first one, I tried this first, where I'm adding it here.
Yeah, that should be fine.
Yeah, but it doesn't seem.
So why is it not doing anything?
Yeah.
Does anybody see the problem? How long is your simulation running for?
It's running till 10.
Right, and when does the event happen?
Oh, yeah, that makes sense.
Okay.
Yeah.
Okay, so now why don't you try
Yeah.
adding the other line? I can't tell you how many times I've done things like that. It's so easy because you focus on the line that's important,
Yeah.
and so did that work now? Do you want to show us what you got?
Yeah. Oh, wait, it's at sign of time greater than 15, a equals a plus 15, right?
Greater than 1/2. Sign is never bigger than 1. So
Oh yeah, that
the
is
number
true.
between -1 and 1.
Yeah, that's right.
There probably are more elegant ways to get a periodic signal, but that's usually how I do it. Okay, so let's see.
Yeah, sorry.
Okay, so that's you did something interesting, but not quite what I was looking for.
Oh yeah, yeah. Can you see
So-
that slide again?
Okay, sure. I think you type sign of time greater than 15. Time greater than 15 is a logical expression. So that's either 0 when time is less than 15 or 1 when time is greater than 15.
Mm-hmm.
So sign of 1 will probably be bigger than 1/2. So it probably will trigger at time 15, but it's not going to give you a periodic oscillation.
Yeah.
Did that work for you now?
Yeah, I think so. Yeah, it gave a different result.
Okay, let's take a look. Can we see your code for a second? So so it's not sign of time greater than 15, it's just sign of time.
Oh, okay. So,
Sign of time greater than 15, as I say, sign of time greater than 15 is a logical expression. Try running that. There you go. So now periodically, every pi units of time,
mm-hmm.
it triggers, and so you see B goes up, little glitch, up, glitch. So A gets hit once, B gets hit every pi time, 2 pi time. Now, if I wanted to make it, a different time, I'd have to rescale the time in that equation. I could make it, for example, if you divided time by 2 in E4, it'll space things out a little bit more. So in your statement E4, say time divide sine of time over 2. There we go. Now you'll see they're less frequent, so you can control the time. All right, did other people get the same thing? Yes? Okay, great. All right. So there we go. We get something like that. And again, this is this idea of triggering. Each time the argument of the at goes from false to true, it does whatever is after the colon. Now that typically we think of this as happening in terms of time, but we could have some kind of event that's driven by variables or parameters as well. So we could have something like if a speed of car greater than 100 miles per hour, then get speeding ticket. That's not a function of time. And here we were initially changing the value of A and the value of B, but we're allowed to change the values of the parameters too. So what I'd like you to do now is you can get rid of that second one for B. The first thing we'll do is just change, instead of changing the value, we'll change the parameter. So you can comment out that second, the second one with the time, with the sign of time in it. But now instead of changing A to A plus 15, make K1 go to minus K1. Okay, so can people try doing that? Is it clear what the question is? If it isn't, please let me know. So comment out that second event, and instead of saying at time greater than 15, A goes to A plus 15, set K1 to minus K1. It takes a little bit of getting used to write programs, if you want to call them that, using these kinds of functions. But this is something that happens biologically very often. At a given time, something will change in your biological system. We'll come back to that at a constant level. If a level of P53 greater than some threshold, cell dies. So we have a lot of threshold triggered events, and we'll come to those in just a minute. Okay, so does somebody want to show what they got for this one? Somebody who hasn't done, Benjamin, did you get it?
Sort of, but I've got a strange result.
Okay, let's take a look. And if I accidentally call on somebody twice and haven't called on you, feel free to speak up and volunteer. You want to screen share, Ben? And since we're being recorded and live streamed, if you don't want to be on screen, say so. It's no problem. Okay. So let's see what you have. All right, let's look at your code first. A goes to B. Okay. K1 equals minus K1. Okay. All right. And let's look at the simulation. So if K1 is negative, what happens? What does that mean for K1 to be negative? We have A going to B at a rate K1 times A. If we have B going to A at a rate K1 times A, what does that mean?
A reverse flow, a flow from B to A.
And so we know one thing, which is when we have rates where we're losing something, where we're turning A into B, if the rate doesn't depend on A so that it goes to 0, when A gets to 0, we'll have problems. And so if I look in your solution here, you'll notice B goes negative because the rate at which B is being turned into A is not controlled by B, so it doesn't shut off when B goes to 0. So you can see things a little bit better if you change the time of the simulation so it stops a little earlier. So what time was the time you made the temporal change? Okay. So here, this is what happens before you've made the change. And so now maybe run it to 15. And this is another 20 is fine. And this is another thing that I would recommend people do, which is if you, for example, have a crash, suppose there's a C-vote error, convergence error, try running the simulation for a very short amount of time. You have a convergence error and you're running a simulation from time 0 to 100. Try running it from time 0 to 1 and see if it crashes or not. If it doesn't, then run from 0 to 2. Then if it doesn't crash, run from 0 to 4. And try to find out when it crashes and why. Similarly, in this case, there is something happening at time 10. And what was done here was very nice because it showed the long time behavior, which was B going negative and A blowing up. But that might have hidden the effect at around time 10. And so doing this now, I think, is useful. So what you see is that A starts going down and it's decaying until time 10. At time 10, B is starts being turned into A goes up, and the value of B goes down even faster than it was before. And so that is exactly what you would expect from this model. So your model is doing what you asked it to do. Now, whether that's biologically meaningful is another question, but it is in fact doing what you asked it to do. All right. And that's an identical result as far as I can tell to the one that I got when I did it. So I could do something a little bit more creative than this, which is, as I mentioned, very often in biology. In fact, in general in biology, biological systems don't know about time. Time happens. We have things that you have chemical reactions, but typically there's no wall clock. So we measure time by the rates at which things happen, and we typically trigger events by levels. As I say, P53, which is a protein that's associated with cell death. If P53 level above cell death threshold, kill cell. If the level of retinoic acid is above a certain threshold, cells differentiate. If the level of cyclin, well, I have to think about which cyclin is bigger than some threshold, the cell divides. And so typically we have things, if we're thinking about doing things to assist biological system from our world, from the outside world, from the lab world, having things happen at particular times makes sense. 1 hour into the experiment, we added the medicine. But in biological systems, they don't know time, typically. Time is represented by chemical concentrations. And so it's much more common then to have systems that trigger off of the levels of variables. And since the at statement depends on a logical operator, a trigger, we can trigger off of levels just as well as we could trigger off of time. We could say if P1 is less than 1, trigger. Or we could ask about the relationship between two variables. If P1 is bigger than P2, trigger. P2 is bigger than P1, trigger. So let's try that. By replacing your statement E1, your E1 statement by saying at A less than 2, K1 equals minus K1. So this is going to, remember, A is decreasing in time. At some point, it will cross the value of 2. What's going to happen? Give that a try. Is it clear what I'm asking you to do? So in a sense, what this series of little exercises is about is trying to think about how to build control systems that think biologically, that are based on things that biological systems have access to. Okay, let's see, who haven't we told on yet? Delaney, did you get, what did you get? Are you there?
I actually joined the Zoom like an hour late, so I am still trying to catch up a little bit right now. I'm so sorry.
No worries. All the code you need is here on the screen. So I hope that
I can show my
okay.
work. If,
all right, let's
right, hold on.
go ahead.
Here we go. Okay, I've got it on this second plot here.
Great. I know you said you were having some trouble with your audio, but that looks great. So this looks very similar to what we had before, except instead of triggering off the time, we're triggering off the value of A. Did other people get something similar?
Yeah.
And I see you've been sophisticated and you've used the layout so that you can compare the one with the trigger and the one without, which is a nice way of doing it. So that's a good. I have to say I always find the subplots confusing, and they're very useful, especially when you're going to do projects. Having those subplot commands is useful. It might be worth actually sharing that example with your classmates, because I suspect they'd all appreciate having the ability, a simple template to do multiple plots in the same line. So I appreciate that.
Yeah.
Okay, anybody else, any comments, questions about that? Thank you very much. So yes, so here we got this one, and you might want to try playing a little bit with those conditions. You might say what if A is less than 3? What if I add a constant value at that time instead of changing the parameters? These are things one could play with. And so now let's do something a little bit more interesting. And this is I don't know, maybe it's a little bit artificial, but we have something now that comes down and A goes to 2, and then A goes to less than 2, and then it keeps increasing. It never comes back. But suppose that when A got to be big, suppose when A is greater than 12, K1 and K1 switches sign again. So what I'd like people to do now is add one line to your simulation, which says that when A is bigger than 12, K1 goes to minus K1. Okay, so why didn't everybody try that and see what we get? Okay, I'll give people another few minutes to catch up. If you're trying to type the code from the screen, there's a fair amount of code in the screen that you don't need to type. You certainly don't need to have the comments. And when I did this, I was adapting old code, and I left in this star $$x0 = 0, which doesn't do anything, doesn't do any harm, but doesn't do anything useful. So you don't need to type that either. So yes, there's a comment about interesting behavior at the peaks over long periods of time. So let's see how people are doing. Wait another few minutes. Again, if anybody needs help, feel free to ask. It's a friendly environment, so we're all here to help each other. Benjamin, do you want to show what you got?
Sure.
Yeah.
Yeah, so that so it's interesting how the peaks are all kind of doing different stuff.
Okay, so that's an interesting question. So the basic, if we scroll down a little bit, the basic thing that's happening here is that initially A is turning into B, and then when A gets to 2, the sign switches and B is turning into A. When A gets to 12, the sign switches again. Notice B goes negative. We're allowing B to go negative here. And then you point out that there's something irregular about the peaks. Does anybody want to take a hazard as to what that irregularity is coming from? Because this is an important thing when you're doing simulations. This is an important thing that you need to try to develop an intuition about when there are issues with your solver. Yeah, good, Drew. Drew makes the comment that you're simulating from 0 to 100 with only 100 intermediate points. And your values are changing significantly over a time scale of 1 time step. And so that means that your time intervals are pretty big. So yeah, so now make 1,000 points. Okay. So now it's much smoother. And so that's a good thing to look at. When you see jagged lines or you see irregularities, when you have sharp peaks, like the one you have for A, typically you need to make your time step pretty small to get something that's meaningful. And so I don't have a perfect set of guidelines for that. But again, if you see that kind of jaggedness or something you think is periodic that's not showing periodic, very often that's because the time step that you're using in your solver is a little bit too big. What if you made it 10,000 points instead of 100,000 points? Doesn't seem to make much difference. But made it 10, what if you made 10 points? That one's pretty obviously not working, right? So you can see essentially the convergence there as you add points. If you have too many points, typically the only cost to you is that the simulation takes a long time. If you really make it a lot of points, so ask for 1,000,000 points, it'll probably crash. You'll have to restart your kernel. All right, try that. Yep. It doesn't know what to do with it. So, but that's a good experience. I'm glad you showed that because it really, those are the kinds of things that you do have to develop some intuition about. And there are rules of thumb for that. I mean, the formal rule is that you don't want the value of your variables to change more than a few percent within one time step, within one micro time step. And exactly what that threshold is, what a few percent means, is going to depend a little bit on how much error you're willing to tolerate in your system. And when you have these kind of sharp peaks like the ones you see here, it's going to be more stringent than it might be if you had very smooth behaviors. But notice that we now have a periodic system. This is essentially a little bit like playing tennis. K positive sends a value down. A value gets to event 1. Event 1 says you're at 2. I change the direction. I hit lob A back. A goes up, it crosses 12. The second event says I'm flipping the sign again and lobs it back. So it's not handed back and forth. And this very clearly shows this idea of triggers going from false to true, because the trigger is reset each time A gets to be greater than a half, greater than 2. That first trigger is false. And so it's primed to trigger again if A ever comes to be less than 2 again. Similarly, for the second one, if A gets to be bigger than 12, it's triggered, and then A is less than 12, so it's false during that whole period. And so you see going false, true, false. So the A trigger, the first trigger is false, triggers to true, false, triggers to true at each bottom point. The second one is false, triggers to true at each top point. You could have a situation where it stays true for some amount of time and only then becomes false. But what matters is the false to true trigger. All right. Thank you for being willing to share that. All right, let me find my controls. All right. In a sense, we're making a mountain out of a molehill here because triggering is syntactically very simple. And you say, what's the big deal? I can write an if statement. If statements are great in procedural code because we know when they're executed in particular sequence. In this kind of thing, in this kind of statement, there's no sequence. If I write at A less than 2 and at A greater than 12, there's no order of evaluation for it. So that was what we got there. So there are a couple of things to say. You can, in fact, write more complicated triggers. In particular, you can say, you can have delays. You can say at time such and such, and then have a wait, and say wait 10 time units, and then do something. Unfortunately, there are no delay equations. You can't write dx by dt is f of x at time t minus 10. That doesn't work. But you can have delays in events. We typically aren't going to need those very much, but they're available if you want to look at the documentation. The one thing that you really do have to worry about in Antimony, and it's actually a bug that we caught, it's supposed to be fixed, but I don't think it's been fixed yet, which is that in principle, the events are independent of each other. So 2 events could trigger at the same time. And that's an allowed thing to happen. You can have two different events trigger at the same time, and it's supposed to work. However, if I have 2 events that trigger at the same time and they modify the same variable or parameter, then one of the 2 events will be chosen and the other one will be ignored randomly. And so if I write at time greater than 15, A equals A plus 10, and I write at time greater than 15, A equals A minus 5, and I run it, sometimes it will add 10 and sometimes it will subtract 5. What you would expect it to do would be to always add 5. Does somebody want to try that out and see what you get? We'll see if it's been fixed in the code in Antimony or not. It's an unplanned exercise. So we can try at, I'll type it in the chat, time greater than 15, A equals A plus 15. Can somebody try that out and tell me what they got? It should give you, it should add 10 to A. And in my experience with that last year, I didn't try it out today, but my experience with it last year, it would either add 15 or subtract 5, but not add 10. Did anybody get a result on that? So you got subtracted 5, you say one or the other, whichever comes first. So for you, when you run it multiple times, you always get the same result, Drew? Okay. So again, the fourth time you ran it, it got 15 plus. So it does seem to pick it randomly. And that's not the correct behavior. The SPML specification says that it should do both. So that's something you have to watch out for. It's a little bit of a trap laid in the code. And we need to remind Herbert that somebody should fix that. As long as you know it's there, you can generally deal with it. But sometimes if you have things like level, suppose you have a time threshold and a level threshold. Sometimes you might have a situation where those two events happen at different times, in which case it'll work. And then once in a blue moon, they could happen at the same time and then it won't work. And it's those kind of intermittent problems that are really hard to catch, especially if they're stochastic. And so I just want to warn you about that. I don't think you'll run into it. I think we ran into it actually in somebody's project where they had two events that should have been happening. That's, in fact, now I remember, it was a project, and it was a project where they were evaluating cancer treatment. And the events were give dosage of drug 1 at time 10, 20, 30, 40, and drug 2 at time 5, 15, 30. And so sometimes the doses were happening at the same time, sometimes they were happening at different times. I believe, can somebody check, instead of typing event 1 adding to A and event 2 subtracting from A, can somebody type the second one, make it apply to B? So instead of having changing A with the second event, make it B. Now I think it should work. Double check that. So then both events. So that works. It's only when you're modifying the same target that it has a problem. Great. Okay, so the other thing that I wanted to talk about is another, you could say, antimony annoyance. And here it really comes back to this idea that antimony is a specification of a set of relationships and not a program. We've seen before that certain things are evaluated sequentially, but that evaluation is done when you do the te.loada of the model. The model is parsed. Whereas things like events are happening at runtime. So all of the algebraic syntax is done at load time, at parse time. And so if we wrote in our antimony, S0 is 100, I equals 10, S equals S0 minus I, S would be 90. If we do M equals te.loada of model, S will be 90. And now we change the value of M dot S0 equals 1,000. We might expect, since we wrote Si equals 10, S equals S minus S0 minus I, that that S would now be equal to 990. It isn't, it's 90. Because this change of S0 was done after the model was loaded, and these algebraic relationships are not repeated. And we've run into that, I think, before. So antimony has syntax that tells it to check repeatedly for values. And that is, instead of using an equal sign, using a colon equal sign. And that basically makes the parameter into a variable that's dynamic. And so if I say S0 equals 100, I equals 10, S colon equals S0 minus I, then if I overwrite the value of S naught with 1,000 and I print the value of S, I'll get 990. The problem is that the time I want to do that, in this case, S0 is the initial value of S. The time I want to do that would have a rate law, which would say S goes to what I, for example, susceptible goes to infected. And if I try to do that, antimony will crash because it'll tell me I've already specified the equation for S, and I can't specify it twice. So if I have S in multiple arrows, in multiple rate laws, antimony knows to add them up. But if I have S specified in an assignment of this kind here, time-dependent evaluation, then I can't have S in a rate law as well. At least on the, I can't have it in the rate law as well. And that causes a problem because I want S to be my initial value. And so there isn't really a good workaround for that. And I'm warning you about that because that's something you could run into when you're doing parameter scans. If you have a series of relationships like this, and I ask you to change the value of S0, you'd also have to change the value of S by hand in the Python. So it's not that's a little bit of an annoyance factor in antimony. And you have to be careful about that. And exactly what the situations are where that works and when it doesn't work, you'll have to explore. In general, Herbert's notes and manuals online are excellent. This is one of the places where I think there isn't quite enough explanation for how it works. But we will find that we need to do this occasionally. So let's try a quick exercise with that. Again, we are not allowed to vary A and B for the relation because that will tell us that there's a conflict between the rate law and the relationship. However, we are allowed to change a parameter. So let's actually change the parameter. Let's take our base code, A goes to B, B goes to nothing. And let's add a relationship, K1 colon equals 0.2 plus sine of time. What happened? Okay, is it clear what the exercise is? So this is a little bit, today I guess we're going to be doing some programming. There isn't that much that we have to do. Actually, Antimony has some bells and whistles. For example, you can define functions with defs and this kind of thing in Antimony. You can define piecewise linear relationships in Antimony. There's some pretty sophisticated things that you can do. If you want to do those things, that's great, but I'm not going to cover them in class. If you learn them well, you can come and teach us how to do them. You can teach all of us how to do them. But again, I typically will refer you for those slightly more sophisticated things to the examples in Herbert's very, very well written tutorials. In fact, if you're thinking about models for your presentations, and here I don't mean models in the sense of the particular simulations, but rather models in terms of presentation, you could do a lot worse than take Herbert's Tellurium manuals as a great way of teaching effectively using notebooks. So I'll give people a few minutes to try this out. And you might, if you finish this early and you want to explore, you could try different relationships. You could try changing the 0.2 to 0.4. You could change the sinusoidal result to something else. You could try taking, combining an event with the sinusoidal driving. Lots of things you can do. One thing that also happened that is that there used to be sine, cosine, these kinds of things, functions are built-ins for Antimony. It used to have a very good set of random number generators, but those have disappeared. They were supposed to be put back, but I don't know if they have been. So it used to be possible to say plus random, and that doesn't seem to work anymore. All right, so does somebody want to show what they got? Anybody want to show what happened with this one?
I could show mine.
Okay. Thank you, Ben.
Okay. This is what I this is what I get first. It's just the normal function. And then in the extra time I also added this event that boosts A every time it gets too low. Makes a fun pattern.
Yeah, that's pretty neat. So you can actually write some pretty sophisticated relationships with some pretty simple concepts. I think that's a very interesting one to combine those two. It also gives you a sense of how biology can do things, because biology doesn't typically have loops. It doesn't typically has thresholds. So those are a little bit like if statements. But they don't have quite the feeling of an if statement because they happen whenever something is triggered. This is what's called computationally event-based programming. And a lot of systems, if you're doing real-world systems, events happen a lot. If the temperature of my car engine goes above 100 degrees, sound alarm. So events are something that very much occur in the real world. often they're handled in classical computer code with interrupts. We have event handlers in Python. We use event handlers a lot for errors. We'll use the try function in Python to wrap something that could fail, so that instead of crashing, we can handle it gracefully. So for example, if you're going to open a file for reading or writing, you'll put that inside of a try, so that if you're not allowed to write to that directory, or if the file doesn't exist for a read, you'll be able to handle it appropriately. The other place that we tend to use events a lot is in keyboard interactions. We'll say, we'll be watching for a keystroke and have something trigger if there's a keystroke. We'll do, when we do sliders using the IPy widgets, all of the slider functions will be written as events. So you'll have some code that runs in a particular way, and there'll be a trap which will be set, which will watch, for example, for a keystroke, or for a click, a mouse click, or a button push, or a button movement. And when that happens, a function will be called. The procedural code doesn't know when that'll happen. It could happen at any time. Typically, what we'll do is create some kind of empty loop that's sitting waiting for that event to happen, but that doesn't have to be how it works. And so I don't know, probably these days, if people are doing robotics or GUIs or any of these other things, you're used to doing event traps. When I was growing up and learning how to code, event traps weren't something that we did so much. The idea of event interrupts in event-based programming was a bit unfamiliar. If you have to do everything built around events rather than for loops and if statements, we do have to think a little bit differently. And so it's an interesting discipline to ask the question, if I want to solve some algorithmic problem and I don't have a for loop and I don't have an if statement, but I have events, can I do it? And here we've shown that we can actually, by doing a pair of events at the top and the bottom of A, we can create a periodic oscillation. So in fact, we've got a loop. And then we can put in some additional event that happens like this one that you just illustrated here, that triggers more complex behaviors. If you have multiple agents that are interacting with each other, that becomes even more interesting. But that typically, again, in this class, we'll typically be writing single programs, not having multiple ones that interact. But that's great. Thank you very much for sharing that. Are there any other comments or questions about these two concepts? As I say, syntactically, they're quite simple. There is this minefield about simultaneity and about overwriting. So we have to be a little cautious when we use them, but they're pretty powerful. And you can do really quite a bit with them once you get familiar with them. So yeah, so here is that example that we saw. Did everybody get something similar? Okay, the last thing I wanted to talk about, great, thank you, Ben. The last thing I wanted to talk about, and I think I mentioned it already, is that the fundamental concept in antimony is a reaction. A goes to B. 4A goes to 6B plus 2C. It's built around the idea of chemical reactions, although we've also been using transformation. S goes to I, V goes to R, these kinds of things. But we can also write explicit ordinary differential equations, only first order ones and only in time. So we want dk2 dt equals 3k1. We can write that with the syntax k2 prime equals 3 times k1. And I'll point out that that would be equivalent to writing arrow with nothing on the left goes to K2 semicolon 3 times K1. So they're not different. One thing that you'd have to remember is that now K2 and K1 are behaving like variables. And so that means that if I specify the derivative of K2, I have to specify its initial value. So I have to say K2 equals 1.0. Notice if I'd written K2 colon equals 3 times K1, I would not then be allowed to write K2 equals 1. That would be over specifying K2. If I write K2 prime equals 3 times K1, then I must specify its initial value. So for the last bit of programming model specification today, let's try that. Let's take K2 and define K2 prime equals 3 times K1. And you could do this in conjunction with the one that we've already got. So let's leave the K1 colon equals 0.2 times plus 0.1 times time. Actually, this one is a little bit different. I had the sine wave before. So this is a bit different. You could leave it as a sine wave. And then K2 prime equals 3 times K1. And remember that you have to set K2 initial value. You could set it equal to 1 to begin with. So why don't you try that? And then that'll be the end of our little set of programming exercises for this afternoon. Looking at this now, I think I actually probably meant to write sine of time rather than time there. So somebody who wants to try it out could try sine of time rather than time. Be more interesting. One thing that this grapples with a little bit is what's the difference between a parameter and a variable? And in principle, Antimony has a distinction between parameters and variables. If nothing else, when you write S equals m dot simulate, the variables are given as output in columns, and the parameters aren't. If you write K1 colon equals something, you'll discover that it's turned into a variable and put in a column. Same thing for K2 prime. Okay, what do people get from that? Anybody have something they want to show for that? This was the one case where I didn't actually run it in advance to show the result. As I say, I think in this case, it's not so interesting because the sign of the sign, not SIN, but SIGN of K1 is constant. Which is why I think I originally wanted to write SIN of time so that it would go positive and negative. Because at this case, so this K2 is equal to prime is equal to 3K1. So K2 will increase rapidly, in which case the disappearance of B will get faster and faster. So it's a little bit more interesting. If somebody wants to try it, instead of writing K1 the way we did it here, I would write K1 colon equals 0.2 plus 0.1 times SIN of time. Semicolon like that. Does somebody want to try that and then show us what we get? That should be a little bit more interesting. Anybody willing to show us result for that? Josh, how about you?
I can. I don't know if it's correct. I just
Okay,
did
great.
what's on the screen.
Okay.
Oh, I
go
can't
ahead.
share while you're sharing.
No, that's okay. That's fine.
Okay. This is what I got.
Okay, so you'll notice that K2, let's see, is that with, I'm a little surprised, is that with, did you rerun it or is that with 0.1 times time? Okay, it's still that, all right. Fine. You'll notice K2 is displayed as a variable, right?
Yeah, I got that too.
Okay, let's just run it from time 0 to 10 so we can see a little bit more detail. Okay, so we see A goes down, K2 is increasing, and B is going up and then down again. All right, it's not so exciting. What if we get rid of the K, what if we make K1 just equal to, get rid of this plus 0.2, make it just 0.1 times sine of time. All right, let's see what happens there. Oh, I see what happened. What's going on here? Why is this not working? This has to have the K1 has to have a colon equals. Otherwise, it's not reevaluated. K1 has to be colon equals 0.1. And you're not allowed to have a space. It has to be K. There you go. There you go. All right. There we go. So now you could add the 0.2 back. There we go. And now you could make your time interval. Yeah, so you see the wavy. All right. So again, I mean, the presence of these different kinds of equal signs is sometimes a bit confusing. It's easy to overlook those kind of things. And so one has to be a little bit cautious with that. Again, it's also not something that we're unfamiliar with, in the sense that in Python you have the difference between an assignment equal sign and a double equal sign for logical comparison. C++ has the same thing. So the fact that there are different equal signs meaning different things is not something that's unfamiliar, but it is a bit of a trap. It's easy to miss that we've typed colon equals when we meant equals, or equals when we meant colon equals. In particular, in the context of antimony, equal sign means that it's evaluated only when you do load A. Colon equals means it's evaluated all the time. And that's the difference between load time and runtime evaluation is something that may not be familiar to people unless they've done certain kind of coding before. So that may be new. All right. Okay. Are there any other, let me come back to our screen deck. Okay. Are there any questions about these aspects of antimony code? Or again, I know that these are sort of very simple examples. If you look in Herbert's textbook or in the online manuals, he's got lots more examples of how to do these things. But I hope that gives you a flavor for some of these kinds of control that are possible. So I think we'll take a break. It's already 7 o'clock. Let's take a 7-minute break. We'll be back at 7:15. And then why don't people think about whether you'd like to continue talking about SCIR models, or if you would prefer to try to solve that homework problem together. And Josh, if we're going to solve that homework problem together, I'm going to need your help on it to make sure we get it right. Okay.
Yeah, sure.
Let's, I may actually have you do the coding on the screen while we work together. But everybody think about that, whether you'd prefer to continue with SCIR models or whether you'd all like to work on that homework problem together. And you can vote in the chat. Just at 7:15, each of you just says homework problem or SCIR, and whichever is the majority, I will go with. How's that? Okay, so I'll see you back here in a little over 5 minutes. Ryan, homework. Okay, so I guess there's a consensus. But let's come back to the homework problem. The homework problem was, let us take the SIR model and we are going to start with one infected individual, and we're going to calculate the probability that we have extinction of the epidemic. And we're going to evaluate that as a function of R naught. So, Josh, are you willing to try doing this live?
Sure. I mean, it's gonna be on the fly, but sure.
That's okay.
You're gonna have to walk me through what the exercise is intended to do, because
Well, I was just thinking maybe it's easier to do it. I was trying to think maybe it's easier to do it. Do you have the code that we had with the stochastic model that we did, the stochastic SIR model?
No, I don't. But I'm looking for it. Just one second.
I mean, maybe I could pull it up too. We could do it together. I mean, we could do it. Let me grab it. Give me 1 sec to get organized here. Okay. Okay. So this problem should be available. The base problem should be available for everybody. We called it lecture 5, exercise 1, Gillespie. And I'd like people to load that, and let's try to do this together. And let's take a minute, make sure everybody has that running. Do people see the NanoHub screen and then also the problem? So I'm going to turn the print off here. So this ran the simulation, this code ran the simulation 10 times. And then overlaid the plots. And sorry, you said I don't know how to get that off. Can you be a little more specific? Oh, you mean
The reaction by my name. Sorry.
Oh, okay. Sorry. I thought you were talking about the simulation. Okay. Sorry about that.
No, I just didn't want you to think I was telling you to speed up, but
That's okay.
Sorry.
I could try that.
no.
Actually, in this case, I'm not sure I could do that because I haven't done this. So let's see. So let's look at the simulation. And what we want to know is whether things, but let's make sure everybody has this running together. So does everybody have this loaded and running? Because I don't want to, I don't want to go forward until everybody has. Okay. And I turned off the print because the print is awkward. And then here I started with 5 infected individuals. Let's start with 1 infected individual. So let's run it. And you'll notice that if I run it starting with 1 infected individual, sometimes the infection doesn't take off, and sometimes it does. So the first thing we need is a criterion for a failed infection. And we have to decide a little bit what that criterion is going to be. But let's say that we say the infection is failed if 90% or more of the people are uninfected at the end. Is that a reasonable criterion? You have to tell me. So let's actually put that criterion in. So let's say if m dot s divided by m dot s0, that's the fraction uninfected at the end of the simulation. M dot s is greater, divided by m dot s0 is greater than 0.9. Print extinction, else print epidemic. Something like that. Is that reasonable? So let's try that. See what we get. So we got epidemic, extinction, epidemic, epidemic, extinction, random. Now clearly our criterion for extinction could be different, but that's perhaps not an unreasonable. So why don't we try that? Make sure we all have that. And now let's actually count the number of occurrences. So let's set number of extinctions equals 0, because we need to some place to count how many extinctions we have. And if we have extinctions, we're going to say num extinctions plus equals 1. And then at the end of this, we'll print show and we'll print number of extinctions. And I'm missing an S. Okay, so now we're running the simulation 10 times. We're calculating what fraction of, and we could, if we want to make it a fraction, we'll divide by the number of times we ran it. So divide by 10 is the fraction of extinctions. Or probability of extinction, because that's what we called it in the experiment. Probability. All right. So we run it once and we get probability of extinction of 0.4. We'll run it again. 0.3. Run it again. 0.4. Okay, can people follow that? So what I'm trying to do to walk you through this is the first thing I want to do is I have to have a criterion. I want to know what the probability of extinction is. And so I have to have some criterion for that. So I defined a criterion that 90% of my population is uninfected at the end. not unreasonable. And then I'm going to run it 10 times. I'm going to count how many times I had an extinction, and then I'm going to display that as a fraction of the number of times I ran it. So I think that that's not unreasonable. And now, in principle, I want to change the value of R naught. And remember, R naught is equal to n gamma over mu. So I have to, if I want to specify R naught, I'm going to have to change one of these parameters. Probably I'm going to change gamma. And so I have to reverse things. So I have to say, suppose I set here, I set R naught equal to 2.5. Then to get to set the value here inside of the loop, what do I have to do? I say R naught, I want to get gamma. So I set m dot gamma 1 is equal to, looking over here, gamma 1 is equal to R naught times mu divided by n. So that would be R naught times m dot mu divided by n, m dot n. And so that will now give me the value of R naught I want inside the simulation. Let's try that. I notice R naught's 2.5 now. Let me make, suppose I make R naught 5.0. Make sure it worked. R naught shows up as 5. Probability of extinction now is 0.1. So it does seem to depend on that. So now I have something where I can loop. If I change the value of R naught, run this, it'll give me the probability of extinction for that value of R naught. So I could print here, I could print R naught equals comma R naught, comma. And so now I have returned, for R naught is 5, the probability of extinction is 0.1. So why don't people see if they can get something like that to work? Take a minute or two. Again, there are plenty of wrong ways to do it. There are many right ways to do it. So you don't have to follow my lead. You can think about this on your own. But now if I change R naught, this will return to me the probability of extinction. And so now now I have to do a stack so I can actually display it. But let me give you people, I'll give people a little bit of time to try to catch up with that. But I'm trying to walk you through how I think about solving the problem. So the first thing I do is I want to calculate, I say probability of extinction. The first thing I have to do is define extinction. So I have to have some criterion for whether I had extinction or not. The second thing I have to do is calculate over repeated runs, what fraction of those runs led to extinction, which was the second thing that I did. The third thing I have to do is say, I want this to be a function of R naught. So now I have to be able to change the value of R naught in my simulation and report the value, the probability of extinction as a function of R naught. And again, if this is confusing or you have better ways of doing it, or I did it wrong, please say so. because I'm definitely doing this on the fly myself. Okay. Okay, great. So now we have to do our usual game of creating a place to put our results. And so let us create an empty array. So we'll do, and this is always the most annoying part, is the array manipulations. We'll say, let's call it results equals, and we have to look it up. I was just looking it up while you were doing that, because I always have to remember the syntax. A numpy, and we want to do empty. I sure better check that numpy is loaded here. I didn't load it, so I better load numpy. Import numpy as NP. We'll create an empty array, and that always have to remember the syntax. It's shape equals square bracket, rows, comma, columns, like that. Because we want the first row, the first element of that to be the value of R naught, and the second one we want to be the extinction rate. So that'll give us an empty array, create empty array for parameter scan. And we could perfectly well have used the code that Josh and Giuliano shared. Okay. And now we need to have a loop where we're going to change the value of R naught. So we'll use for R naught in, and now we'll use we have to use numpy a range because we want to loop over values of R naught. We'll do numpy a range. And it doesn't, how to say it, it doesn't, well, I always think it's funny that Python doesn't have a regular a range version. And let's set, looking at our picture, we want R naught to go from 0 to 5. And let's do it in steps to begin with. We can use coarse grain steps because we don't want to take too long. Now we have to indent everything, and I don't remember if there is a doesn't look like I have an indent function. So I may have to indent them all by hand. No, indent tab works, so I can indent. So now I'm going to change my value of R naught outside of in my loop. So I don't want this R naught set here. I put my comment in the right place. And so now it should give me, and the print statement should be inside my loop too. So if I now run it, it should scan my values of R naught and tell me what the probability of extinction is. I probably don't want to do all this plotting because it's going to be hard to see what's going on. And I probably don't, well, I'll leave the prints here for the moment. So let me run that and see what happens. Oops. Oh, didn't comment out both pieces. Okay. Well, let's see what happens. So R naught 3.5, probability of extinction, R naught 4.0, probability of extinction. Looks like I'm getting not very exciting values, but I'm getting something. So why don't people try to add that? This is a point where I may not be doing the best job of writing this program, but let's try that. So I'm looping over R naught, and I'm calculating the probability of extinction. At the moment, I'm not plotting it or doing anything with it. I'm just printing it. And I'm not sure how I get a probability of extinction of 1.1. Oh, because I went from 0 to 10 to 11 instead of 0 to 10. So I actually had that wrong. Okay, everybody got that? And so now then what I have to do here after my print statement is I have to stack this. And so I could use VStack, or I think I can use numpy append also. So let me try append. So the append, numpy append, I want to add my R naught comma result to the end of my array. And so I can do npy append. And then I need my array name, which was results. And then I need to have the thing that I want to append, which would be R naught, comma, non-extinctions over 10. All right, and then once I'm outside of this, I would do a te.plot array. I want to display it, plot array results. Let's see what that looks like. Well, it didn't work. Why did it fail? It failed because I'm not used to using the append. So I must have done the append wrong. Let me do the VStack, which is the one I'm used to. Results equals npi dot VStack of results.
Drew put how to append in the chat.
Well, append didn't work, so let me see if the VStack works. And I've got, I just VStacked it wrong. Josh, you're my consultant on this. What did I do wrong?
1 second.
I was trying to use append because it should be simpler.
Let me see what the error is again.
The error was the size, the positional argument. I've got, probably has to all be in square brackets, doesn't it?
Oh no, they have to be inside another set of parentheses. You're missing one at the end.
All right, there we go. And let me try doing that with the append. I think it's actually more or less the same. I think it's results equals npi dot append. And then it would be results, comma, R naught, comma, and then a number of extinctions divided by 10. I think that should do the same thing. Let me try it. Nope. Couple index out of range. So I'll have to play around with the append because it's not the one I'm using. So again, what have we done? We've created a place to put our result, which has 2 columns, no rows. We've calculated R naught. We've calculated the probability of extinction. And now we're V-stacking it into our results and then plotting the result. So let's see what we get here. And we get something that's not real pretty, but not totally nuts. So let me give people a chance to try that. See how you're doing with that. Okay. So I'll give people some more time to work on this. But one thing, if you're inside of this, if you're done with that already, one thing you might want to do is if you want to make this prettier, you might do two things. One, you might run more than 10 replicas. And if you change the number 10 here, you have to change that number here as well. So you probably want to make that a variable. It's defined outside of the loop. And the second thing you might want to do is the time we're running to may not be long enough for the thing to converge. Although actually for this problem, it's probably okay. But if R naught is near 1, this will give a wrong answer because because it takes time for the infection to get propagating. And so you might, for a threshold of 0.9, a time of 40 may be too short for R's, just around 1. And so we might actually want to adjust our time as a function of R naught or our threshold as a function of R naught if we were being fancy.
Mine is doing the opposite.
Your probability is going up as R naught goes up.
Yes.
Okay. Did you put your threshold as m dot s greater than 0.9 here?
Yes.
Okay. Well, let me just do you want to show that to everybody, or shall we do a little thing first? Okay. Okay. Well, that doesn't look like it's doing anything. Let's see, MS. Okay, extinction. Okay, that's reasonable. Epidemic. That all looks pretty reasonable to me.
No, that's correct. Okay.
Yeah, you want that to be that has to be inside your loop for the R naught.
Mhm.
And then you have to run it. Yep, that looks reasonable. Oh, typo. Gamma 1. See if that fixes it. There we go.
Wonderful. Thank you.
No worries. That let's see if I can find my. Oops. That's an interesting screen share. Let me stop the screen share. All right. What are you seeing?
All of us
Oh,
in the squares, all of our names.
okay.
Oh, we were seeing the two screens for a second.
I don't know why did we do that? It's an interesting. Okay, why? You would think by now I would know how to use Zoom. Huh? All right. So let me see if I can get the screen share to work. Screen 2. Share. I'm sorry, guys. I'll just do that. Let me try it again. Is it okay if I just share the notebook for the moment?
Yes.
That seems to work. There's something funny about sharing that screen that it keeps pushing. It keeps throwing the display up, and I don't know. I don't want to. We're running out of time, so I don't want to waste your time. Okay, so now we have our basic result. So let us do a couple of things. First, we can make our step size a little bit smaller so that we get something that's more continuous. And let's turn off the print here so we don't chew up so much screen space. Okay, so now we see something going down. It's noisy though. And so now to make this work better, we'd have to run more replicas. So let's create one variable, which we'll call, say, number of replicas, which will just be how many times we're going to run the loop. And so let's make that 50 instead of number of times per value. So let's put that in here. So we'll make this replicas. And we have to then also, we need to make that here also. Instead of 10, now we have to do float of replicas. We have to normalize by the number of times we're iterating. All right. And let's turn off that print and give it a shot. What happens? That take a little while. Well, it's getting better, I think. It's not perfect, but it's not too bad. So why don't people, we're out of time, but does this give people something they could play with to try to get it closer to being what you have here?
Yep.
What I would suggest doing is you can try increasing the number of replicas. That should make it less noisy. You can have the simulation run for longer as possible. And you can play with this threshold. But if we look at the basic results for R naught below 1, we get 1. Interestingly, it starts going down for R naught still less than 1, which is a bit of a surprise to me. It goes down, whether it's this nice parabolic curve, I can't tell you. It's a little bit noisy to determine that. But it seems to level out around 0.2, which is what happens here. And so I would say that this is pretty close to what you need. If somebody handed this in as a homework assignment, I would give them 10 points on it. Now that you've seen this, I expect you to do a little bit more to see what's going on. But I think that you could, so for example, we could play with this. What happens if we make our threshold 95% instead of 90%? It actually makes things a little bit worse around 1. But if we made our threshold 80%, that's getting closer to what we see here. So we could play with the threshold. We could play with the number of times we repeat. We could play with the duration of the simulation. we made the simulation run for 100 times, up to 100 times steps instead of that. And so you can do that, all of those things. And again, since it's a stochastic simulation, you expect there to be some fluctuation. So I'll tell you, as soon as I am done with the class, now 8 o'clock, so we're done. I will send this around to everybody as something you can play with. And again, I think in general, watching me code is not that edifying. I hope people were able to follow along. But I think walking you through the steps that I would go through of analyzing the problem. So start out with probability of extinction. Well, first we have to say what we mean by extinction. Then we have to calculate the probability. Then we have to vary our knot and see what happens. And then we have to put it into something where we can plot, and then we look at what the things control the results. So that's the kind of thought process that I hope that as we go through the semester, you get to be more able to do on your own. I know it takes time to work on it, and I get stuck on it too. So it's not that it's something that's easy to do. So, all right. So I will try to, I probably won't get homework out tonight. I'll try to get a homework out for you tomorrow or at latest Thursday for this week. As I said earlier, I'd like to give an assignment, which is to do a little run and review some of the previous semester's course projects to give you a sense of what you think works and what doesn't work.